Next subject is phase recovery in Gabor holography. Uh, Digital holograms can be captured in different configurations. One of the oldest configuration is Gabor holography. Gabor holography is very simple, and there are not so many optical equipments because, like I said, optical equipments are expensive. So the best way to reduce the cost of microscope is to reduce the components of these microscope devices. But the problem with the Gabor holography is that it suffers from the superimposed noise. When we say superimposed noise, is that this virtual image and real image, they are superimposed. So when we focus on the real image, we see this unfocused virtual image. When we focus on the virtual image, we see this unfocused real image. Okay, let me show you here. So the left side here is a reconstructed phase image, and then we see this red blood cell with this donut shape. If we record the same image with this Gabor holography here, we can see that the shape of red blood cell is kind of weird here because there is distortion in the shape, because like I said, there is a superimposed noise because of virtual image and real image on this phase image. To provide this image, we use some simulation to obtain exact same the Gabor holography from the off-axis holography, which I'm not going to detail so much. I just go into this deep learning model. So in A, you see a Gabor hologram. B, we see a reconstruction of A. And you see the cells are not really observable because there is noise. And if we want to have the clear picture looks like C. So what we used here, what we did in this work is that we try to convert B to C with deep learning. So okay here, this is the general scheme of this model. We use a Gabor hologram, and we use frame propagation, which is the numerical reconstruction. And then we have this reconstructed phase image from the Gabor holography, which has a lot of noise inside. Then we use this UNet model, which is a generator of a GAN model, to recover this model, and then we get noise-free quantitative phase images. So A shows after digital propagation of Gabor hologram, the phase image is fed into a UNet generator. In B, we see this the Markovian discriminator, which is a patch GAN. What it does is that it divides one image to the patches, a Markovian discriminator or a patch GAN divides it into the patches, and then it compares the distribution of each patch to the other patch of the other image, and then provide us some fake and real image. So what happens here? We fed this one, the Markovian discriminator, with the concatenation of these two images. One is phase image obtained by off-axis digital holography. This is the ground truth data. And the other one is the generator output, which is a noise-free image. The image size is 768 by 768. And this Markovian discriminator provides us real or fake. So in this study, we use two models. One is for the red blood cell phase recovery, one is for the cancer cell phase recovery. Okay, so during the training, this model tries to learn the distribution of this input and output. And it learns it in epochs. So in epoch 0, if you look at this red blood cell, these are the red blood cells. This is the shape of red blood cells, epoch 0, then epoch 10, epoch 50, epoch 100, epoch 400. And it gradually tries to learn this red blood cell. And here we have cancer cell. There are two types of cancer cell in this study. And this one also shows the development of the model to recover this phase image of this data. And this one in the B shows us this normalized loss of discriminator and generator for the red blood cell, and C shows us normalized discriminator and generator loss for cancer cell. Okay, let's get some, let's see this one on some live images. But before that, let me explain this one. Another advantage of this deep learning model is that it can recover the it can also recover the cells that are not in focus compared to the other cell. For example, here, this cell is not on the focus comparing to the other cells because it might be a little bit higher or lower compared to the other cell relatively. And also here, and in this case, this model also is able to recover this type of noise or distortion in the image. And there was something interesting we found out is that when we have, so we trained this model with two type of red blood cell, with two type of cancer cell, but it was also possible to see these cancer cells which are not used for the cancer cell line, which are not used for the training. For example, we used a skin and lung cancer cell, but we were able to recover a bladder cancer cell with this model. And here on the right side, we see this Gabor phase image, and this Gabor phase image, which is noise is removed by GAN model. And as you can see, there's a lot of noise here, and there is not so much noise here. This is a cancer cell growing up, and then they divide into two cells when this is a time for them to divide. Usually it happens in 24 hours. So if you look at this one grows up, detach, and then divides into two cells.